And then using regular paths, we defined something called the curves actually. Okay? And then by defining the curve, then we started studying different kind of properties of the curve, that okay, if you take two curves, how you can connect them and make new curves out of it actually. Okay? And then we said that how you can define a scalar field on a curve actually. Okay? So what is the meaning of a scalar field of a curve? That you take a point and then associate a scalar to each point of a curve, and that would be the scalar field on the curve. And before that, even we defined that what would be the meaning of measuring the length of the curve. Okay? And what would be the meaning of integrating under the curve, under this twisted curve. And we find a scalar field on C. And then we defined that how to integrate the scalar field on C. So if you have a scalar field on C, then how you can integrate it. Okay. Then we defined how to define the vector field on the curve C. Okay. And then we defined and talked about and studied really that how to integrate vector field on the curves actually. Okay. And then we mainly proved two big results, okay, which says that. And then we also define what we call the double integral of function actually. Okay, so what is the meaning of this? Okay. And then we proved something what you call the Green theorem. Okay. The Green theorem is serving two purposes, is that it's connecting these two species actually. Okay, one thing. And the second thing, Green theorem is telling you that if you take a region and collect all small curls at each point in the given region, then so imagine you have a region, okay, and you take all these points and compute the small curves, local curves, and add them up. Their sum is going to give you the total circulation of the F along what you call the C. So imagine you have this curve and a vector field F is defined on it. So if you compute the circulations, local circulations, and sum them up, then you're going to get what you call the net circulation of F around the boundary. Okay, that was Green theorem. And then we also proved and studied and used actually what we call the divergence theorem actually. So that says that if you have such a region and you have a scalar field defined here and it's diverging out, okay, then the net divergence, okay, that is happening in this region is going to be equal to the line integral, okay, of F of the vector field F that is exiting in the normal direction through this boundary. Okay, so you want to know how much of the divergence is going on in the region? Look at it, that how much of F is exiting in normal direction, okay, through the boundary of the curve. So that was the key thing. Okay, and the divergence theorem that we proved, the planar divergence theorem, okay, that we proved basically also connects the line integral with surface and double integral. And then in the next chapter we spend on that how to compute the double integrals. What are different techniques actually? I mean, imagine if you have some crazy double integral, how to compute it actually. Okay, so maybe you have to do the substitution, the kind of substitution you were doing when you were doing the one-dimensional calculus actually. Okay. So in the next chapter we learned it. Now what we want to do, we want to do the precisely same stuff, but now we want to do for the surfaces. Okay, because intuitively, I mean, if you remember, we saw that if you have a curve, for example, defined on a line or on an interval, okay, you have a curve, and then you combine the copies of all such curves and bunch them up, you're going to get a surface. Now the question is, how to do do all this stuff on one curve, I know it. But now I want to do how to do the same stuff on, what do you call the bunch of the curves or the surfaces actually, which is a combination of it. So from where we start. So here we started with the path, so we're going to also start with the path for the surfaces. Same thing. So here we say the curve is defined through plot. So here we said that you have regular paths, we can also define kind of regular paths for, not really going to be paths, but analog to regular path for surfaces. Then we know that a curve can be defined in the terms of the regular paths. So we'll define the surfaces in the terms of the regular, whatever that thing would be that we're going to define. So that would be parametrization basically. And then we're going to say how to define a scalar field instead of curve on a surface, and how to define a vector field on a surface, and how to compute the integral of it. And maybe we will also, in the middle way, we're going to see. So here we talked about the length of the curves. Now we're going to talk about the surface area of the surfaces actually. So if you have a surface actually, how to compute the surface area of it. Okay. And then defining scalar field and vector fields on surfaces and how to compute their integrals. Okay. And then we're gonna, do something similar. So we're gonna prove a Green theorem version of, 3 dimensions. So in other words, instead of, for example, a planar region, you have a volume now, and there is curve going on within that volume. Okay. So we're gonna prove a version of Green theorem for 3 dimension actually, or a dimension for the surfaces. Okay. And then, and then we're going to also prove a version of divergence theorem. Okay. So the version of Green theorem in case of surfaces we call it a Stokes theorem. We already heard the Stokes theorem. We're going to see that will be on the same lines. Okay, there will be bit different things, but it will be very much analog. Very much analog. Okay. And this, learning this consistency is important actually. Because, for example, when you want to do serious physics or higher mathematics, you're going to develop calculus on manifolds actually. So the manifold is a generalization of surface. So the surface is an example of manifold. Okay? Curve is an example of manifold. So you can define all this stuff in a similar way on really very abstract objects. Okay. So it's important to see the consistency. So let's start. So from where we should start. So let's see what's the analog of the path is actually. Okay. So do you have? Yes. So I hope you got a get picture, and that's what really the agenda for the end of this course is going to be. All right. So recall, if you have a path, let's start with the path actually. Okay. Imagine you have this interval, say A to B. So you have this, for example, this x, y, z axis. Okay. And I have a path actually. Okay. That takes values, for example, from an interval A to B into, say, an R3. Okay? And you define it in this manner. So P of t is what? Is 1t cube and t square. Okay? 1t and t square. So how does this is going to look like? We have discussed it really in the beginning of when we were talking about the curve. So the one thing is for sure that this curve is going to be attached, because x is not changing, so it's going to be attached somewhere here. Okay. And how it's going to look like? So it's going to look like this. So what is the name of this curve? Goes like this. What was the name of it? So it's a cusp actually. You remember? And we saw that in this cusp, like this point is a troublemaking point. And now I'm saying, let's assign a cusp to each point of the point. So here we kind of defined and assigned a cusp to one. Okay. So I'm saying let's assign the cusp to the each of, for example, point on the x-axis. So what you're gonna think that what kind of picture you're gonna get. Okay. So it would be like an open book actually, roughly like that. Okay, the Neely parabola. So let me draw a picture of it. Alright. So similarly, let me define, for example, let's consider a P, okay, that takes say 2 inputs to UV. Okay. That takes 2 inputs to UV. Okay. And give you this. So it takes this point U, okay, on x-axis, and on y-axis it has these values. Okay, so what are the values? V cube and say V square. These are the values. So how does the picture of this is going to be look like? So U V square is really an x, y, z axis actually. So U is 1. So like this picture is just one manifestation of it actually, that you take U equal to 1, okay, and then you're going to get this curve. But now the U is arbitrary, so in other words you can take any point as U. So how does the shape of it is going to be look like? So the shape of this is going to look like something like this actually, okay. So forgive me actually, so it's going to be something like that, okay. So it's going to be something like that. Okay. By the way, what does this U is representing? That there is some domain of it in 2 dimension, and in 3 dimension you are assigning the points of it. As this spike was a trouble, okay, can you see that this is also going to be a trouble? So what was wrong with that spike actually?
Not integrable.
That if it's not about integrable, it's not differentiable. If you try to compute the derivative of it, okay, maybe you can compute derivative, but it can turn out to be 0 actually. Okay. How about this one actually? So here you have this PUV. So let's compute say PU. So let's compute the partial derivative of the U actually with respect to in U direction. I'm going to talk in a bit more detail that what do you mean by U direction actually. Okay, but let's assume for now that okay, since P depends on U and V, so I'm just computing the derivative of P with respect to the U. So what would be PU? It's going to be 1, 0, V cube and 1, 0, 0. Okay? So what would be PV? Partial derivative obviously. Okay. So it's going to be 0, PV square and 2V. I know this guy can't be 0 for sure, because it has one component that would never be 0, but this guy is 0.
When you put 0, why V0 then?
So on what points of the plane this would be 0?
Origin. Origin.
U equal to 0.
Origin.
Only origin. So it's these points actually, all points. Okay, so what should I put here so that it becomes, for sure that second component of the points is going to be 0, because you want to make these 0. But how about U? Is there any restriction on U? U can be anything. Okay, U can be anything. Negative point. So in other words, you take PV is a function of U and V, and substitute U0. So what would be the outcome?
0, 0.
You're going to get 0, 0, 0. So this strip of the points, this line, okay, is really a trouble-making strip actually, okay, which is turning derivative into, what do you call 0. There, in case of one dimension, we were very much interested in regular curves actually. Why we were interested in regular curves? So that we can talk about the non-vanishing velocities of them actually. So P prime of t must be 0. In other words, that you are assuming that if the curve is representing the trajectory of a particle, the particle is not stopping anywhere, so it's really producing a curve, okay, without a gap or a troublemaking point. Okay. So if I have this kind of an object, then this is a strip of the points which are troublemaking, because this would be 0. Okay. So what we did there actually to meet with such kind of a, so what you can do with such kind of situations, if you have a parametrization that is giving you such singularity, it's a singular point. Okay. I'm going to define it precisely. So what we did there, so we reparameterize it. So you can do the same thing here. So let's reparameterize it. Okay. So one of the possible reparameterization of it could be this actually. So imagine that I'm defining a new reparameterization Q of uv, and that is defined through P, but in this manner, P of u minus v, say, okay, and u plus v. Okay. So I'm defining a new parameterization of it, which is Q of uv, and it's what you call P of u minus v and u plus v. So what would be P of u minus v and P of u plus v? So it's going to be u minus v and u plus v q and u plus v square actually. Okay, it's a bit of such kind of a map actually. Okay. Now, what would be Qu in this case? You're going to see if you compute the Qu, the partial derivative of the u, so that's going to be 1 3 times of u plus v square and 2 times of u plus v. Okay. Now this one guarantees that this will never be 0 no matter what u and v you choose actually. This will never be 0 because the first component is fixed actually. And if you take say Pu, okay, so it's Qv, so the Qv is going to be
minus 1
3 times of u plus v square and 2 times of u plus v.
It will also lose.
So this will also be non-zero actually. So we can avoid that, as we could avoid the what do you call that non-regularity or singularity in case of the curves, we can do the same actually here by introducing a reparameterization. If you remember, so one interesting thing about Qu and Qv that you can also prove is that they are linearly independent actually. How can you take two vectors and check that they are linearly independent? I'm sorry?
linear combination लिखते जाएगा.
वो तो definition होगा. So that is the definition that is, that is a definition that would be useful when you have, many vectors actually. Okay, so make the combination equated to 0 and try to figure out the constants. But for two vectors you have other.
सर अगर एक वेक्टर को हम दूसरे के स्केलर टाइम वेक्टर लिख सकते हैं तो भी वो लिनियरली इंडिपेंडेंट नहीं रहेंगे.
Linearly dependent होंगे.
हाँ सर फिर वो लिनियरली डिपेंडेंट.
What you can do is that you take their cross product and check their, whether they are, whether they are spanning. In other words, they will be linearly independent if they are spanning some area. Think about it.
Yes.
They are spanning some area. But if they are linearly dependent, they will be like coincident actually. So they will not span any area. So the area spanned by these two vectors is going to be 0. But if they are linearly independent, it is sufficient to show for two vectors that they span some area. And how can you know that they span some area? Compute their cross product and see their magnitude is 0 or not. So if it is not 0, they are linearly independent. If it is 0, they are coincident. ठीक है, समझ आ रही है?
Yes.
Anyway, so linear independence is going to be an important factor in our discussion soon. Okay? Are you getting the point? So here, I mean, if you remember, in case of the curves, if you have one path and you have another path, okay? So if you have one parameterization and you have another parameterization, okay? Then there was a map that takes me from P to Q actually. So what was that? So it was phi actually, yeah? So what do? So you compose P with the phi, okay, and it gives you the Q. The question is, do we have something similar here? So the answer is yes. You're going to have a phi. Okay. So what would be the phi? What is the phi actually that is taking me from P to Q? Can I see Q as something composed with the P? Something composed with the P. So what should be that map that I say? So U minus V and U minus V. So the object that allows you to reparameterize, that takes you from the P and take you to the Q is this map actually. So the phi of UV is U minus V and U plus V. Okay. And now I can say that really the Q of UV is basically P composition phi of, so this phi is an interesting map that is from. Okay. What should be the domain of phi? There's no restriction, it's continuous, so it's R2 to R2. So there the phi was, in case of the curve, was mapped from one interval to interval actually. While here is going to be some region in R2 to some region in R2. Okay, suitable region in R2. It's very much analog what you did there actually. Okay, there is a lot of intuition. Okay. So what you want with this phi? So what should be what good thing that this phi should have actually? Okay. Continuous and so essentially what we need here, if you remember, what you need here that your phi must be a diffeomorphism. So it should be diffeomorphism. That's it. Okay? It should be a bijection. You can always switch between A and B, which are the domains of, for example, domain and codomain of map phi, and it must have a Jacobian non-zero. Okay. So if you want to transform one parameterization, okay, to another parameterization, then you always need a diffeomorphism, or a diffeomorphism is a good choice actually. Okay, because it's going to play a very interesting role actually. Let me tell you what one role this is going to play in the form of a proposition. Okay, I'll just give you a hint of this, proof of hint of the proposition, and then do it for yourself. So here's a proposition that says something interesting. So imagine you have a diffeomorphism phi from V to U, where V and U are two subsets of the diffeomorphism between open subsets U and V of R2. So these are two open subsets of R2. Now if, okay, let P from U to R2 be a smooth map, a smooth map. And if Q is P composition phi, in other words, you construct a new map by composing P with phi, and phi is a diffeomorphism, then this diffeomorphism is going to do an amazing thing. So this amazing thing is this. So what is QU cross QV? What is QU cross QV? Okay, Q and QE at the moment, we're gonna in a minute, interpret QU and QV in a very concrete manner that what these guys are and what is their meaning. But at the moment you can say they are two vectors. Okay? They are two vectors. Okay? They are two partial derivatives, they are two vectors. Okay? They are basically tangent vector in the direction of U and V. Okay? So the QU cross QV is going to represent what? So its magnitude is going to be the area. It's a vector, so it's representing a third vector whose magnitude is going to give you the area spanned by, area of the parallelogram, whose sides are basically these two vectors. Okay. So the QU cross QV is PU cross PV. So what is PU cross PV? So that's one rectangle. Okay, so you can understand it in this manner. So imagine, so the P is representing a kind of a surface. Okay, and you composed it with phi. Okay, you composed it with phi. So phi is going to do what? It's going to maybe change it a bit. Okay, maybe it's going to do something with it, turn into something new. Okay. So the Q cross QV is what that, okay, PU cross PV is what you take a point actually, and there are two directions. Okay, two directions, which I'm going to talk that what these directions are in a moment. But imagine that, okay, this is representing, what do you call, PU cross PV. So that PU cross PV is going to give you its magnitude is going to give you the area of a rectangle actually, whose sides are these two vectors. And what will be the Q cross QV? So it's going to be another rectangle here actually. Okay? Its magnitude is going to give you the rectangle of it. So what does the miraculous thing that phi is going to do is that these two, vectors are related with this number actually, the determinant of Jacobian of the phi. Okay. Jacobian of the phi. Can you see this? The Jacobian. In your previous chapter, you saw that really, if you have two rectangles and you've transformed, under, for example, a diffeomorphism, so it preserves the areas of the rectangle. It not preserves, but it kind of allows you to equate the areas of the rectangles. Are you getting the point? So if you take the magnitude of it, so the area of this is going to be equal to the magnitude of this. Are you getting the point? And obviously, one thing you can conclude as well, that if, okay, let's prove only this actually from. So here's just a sketch of a proof factor. Take a point B from V. Okay. So if you're going to operate B onto V is going to be a point in U actually. So let's take a point phi of A, okay, phi of B in, say, so this is going to be in U. Okay. And let's give this guy a name A. So A is a name.